function. We first need to find the root x using the find method like this, and the root y using the find method. We could use just self.root x. However, sometimes we might change the functionality of this find operation, and we could remove this attribute. Therefore, it is better to use this find method because it guarantees the functionality of finding the root. And after we did that, if they do not match, if root x is not root y, then what we are going to do is for every root, if self root I equals root y, then we're going to change the root of y as root x. And after this operation, the root of y, the elements whose roots were originally y, are going to become root x. Okay, so it is how we unite two elements. So that was quick find. As you can see here, the find operation is very fast, O1. However, this union operation takes time complexity of On. And let's talk about quick union together. I'm going to copy this code because other functionalities are pretty much the same. I'm going to delete this part. So the init operation is the same, and find operation is going to be somewhat different. And the connected operation is the same. We don't have to do anything for this connected method. So how do we perform find operation? We need to find the actual root of x. So what we are going to do is until x is not the root of itself, we're going to keep following the root x. And after this while operation, we could find x. Okay, and if you compare this find operation with that of a quick find, this is much shorter and faster. However, this one takes smaller than On. However, it could reach On in the worst case. And when it comes to union operation, how are we going to perform union? What we are going to do is we first check the root of x and root of y. And if they're not the same, rather than having this for loop, what we are going to do is, so I'm going to make these 3 lines commented. And what I do is change the root of y as root of x. So the union operation compared to the quick find becomes quite simple. So it takes less than On. So these are the differences between quick union and quick find. And at this point, you might think, so which one should you use to implement disjoint sets? Think about it for like 30 seconds and please send me your opinion, which one is better between quick union and quick find. I'll give it 30 seconds. Think about it. Okay, thank you for sharing your answers. The answer is quick union. Why is it so? We need to think about worst cases. In the case of quick find, we're combining O1 operation with ON operation. And when we are combining these two operations, the worst case is ON. So even though we have O1, the effect of O1 will be minimum when we are calculating the overall complexity. So when we calculated the asymptotical time complexity, O1 plus N or O1000 plus N becomes simply ON. We're going to ignore the smaller part. So the overall time complexity is going to be ON for quick find. And in the case of quick union, the overall time complexity is smaller than ON because we're combining these two operations, ON and ON. So in general, we say quick union is better than quick find. However, there is another way of improving quick union. We want to make this operation better. That is called union by rank. So here, we are just choosing X or Y randomly and set one of them as the other's root. However, this could be very inefficient. And what we are going to do is, I'm going to describe union by rank here. So when we are uniting two groups, rather than just simply concatenating two things, what we are going to do is let's say 1, 2, 3. So in the case of quick union, the height could grow like this. However, in the case of quick find, the maximum height is always 1 because all the elements have the same root in the same group. However, in the case of quick union, the height can grow more than 1 like this. So when we are combining, let's say this group and this group, if we combine this one, the first one, to this one, then the height, maximum height, becomes larger. So 5, 6, and 1, 2, 3, 4, like this. However, if you combine this, if you connect this one to this one, then the maximum height does not change because 5 and 6 goes here. So rather than just blindly connect two groups or unite two groups, we're going to think about the maximum height of each group. And we say the maximum height as rank. So we're going to connect the group that has smaller rank to the one that has larger rank. Okay, so that is the concept of union by rank. Okay, so we need to change some implementation to make these operations more efficient. So rather than just keeping track of the root, we're going to keep track of the rank as well. So at the first initialization step, each vertices will have the rank 1. And the find operation is going to be the same, and the connected operation is going to be the same. However, the thing changes is the union operation. Sorry for that. There is some technical problem here. Okay, resolved. So when we are, we need to just change this union operation. Here, rather than just setting the root of y as root x, we're going to consider the root, the rank. So if the rank of x is larger than the rank of y, then what we are going to do is set the root of y as root x. And else if the rank of root x is smaller than the rank of y, then we're going to set the rank of x as the root of y, like this. Otherwise, this means x and y have the same rank. In this case, what we are going to do is we're going to choose randomly x or y. However, here we're going to choose y and set the root of y as root x, and we need to increase the root of x by 1. So by slightly changing the rank operation, this operation becomes much faster. Okay, so this is one improvement over naive quick union. And another improvement we can do is called path compression. So up to this point, we have made this union operation more efficient. And we're going to make find operation also efficient using path compression. So the other operations are the same. However, the find operation is going to be somewhat different. So I'm going to show you one example first. Let's say we have 5 nodes, 1, 2, 3, 4, 5. And the root of 1 was 2, and the root of 2 was 3, and the root of 3 was 4, and the root of 4 was 5, and the root of 5 was 5. And this is 5 was connected to 4, and 4 is connected to 3, and 3 is connected to 2, and 2 is connected to 1. So this one is similar to linked list rather than a tree. And the time complexity is going to be O(n). However, after the find operation, to find the root of 1, we need to go to 2, because the root of 1 is 2. and we go to 2 and check its root. However, its root is not 2, but 3. So we move on, and we reach 5. And the 5's root is 5 itself. So we say the root of 1 is 5. However, after we do this, why don't we just stay there? Why don't we just update the roots of these elements? So after define operation, we're going to update the root of other elements. We can do this, okay, when we are performing this find operation. And this is called path compression. And this is going to be our next PPP exercise. You can slightly modify this operation and can implement this path compression. In this example, don't think about the rank. Okay, so try to implement this find path compression operation